In the last video, we talked about 2 by 2 matrices and complex eigenvalues. And we saw that every 2 by 2 matrix with complex eigenvalues has the form P times C times P inverse, where C is this matrix A minus B, BA, those are the columns. And A and B are the real and imaginary parts of one of the complex eigenvalues. And so what that tells us is that for the purpose of calculating e to the at, we just need to calculate e to the ct. And that's what we're going to do in this video. So what is e raised to this matrix T? Well, the first step is to rewrite this matrix. So this is, the matrix is first column is AT negative BT, and the second column is BT AT. We can write this as this, as the sum. And these two matrices, they commute with each other when you multiply. So if you take this matrix and multiply it by that matrix in either order, you get the same result. That happens when one of the matrices is a diagonal matrix where the diagonal entries are the same. So if you look at this first matrix, you see it's a diagonal matrix and both entries are the same. So that explains why these two matrices commute when you multiply. And this fact that the matrices commute when you multiply imply that when you do e, so I'm just going to write this as exp, just so I don't have to write the exponent in a superscript. So when you do the exponential of the sum, one of the properties of the matrix exponential, this is the minus, one of the properties of the matrix exponential is that when you have a sum of commuting matrices, then the exponential is just the product of the exponentials of the individual matrices. So it's just going to be the exponential of this matrix times the exponential of the other matrix. Now this is a diagonal matrix, the first one. So we know the exponential of a diagonal matrix, it's just going to be e to the at on the diagonal and 0 everywhere else. But we still need to find the matrix exponential of the second matrix. So how do we do that? Well, recall that in the formula, in the definition of the matrix exponential, right, it's defined to be an infinite series, and you have to raise these matrices, this matrix, to a bunch of powers. So we need to figure out what that is. Well, first, so this matrix, I am going to pull out a BT. So this is, well, okay, I'll write it like this. Let's pull out the T like this. So now we have e to the some matrix times t, right? And that's what we want to calculate. And so this matrix, I'm going to pull out a b from it. So it's going to be, first column is 0, negative 1. The second column is 1, 0. And the reason is because when you raise this to a power, say the kth power, it's just going to be b to the kth power times this matrix to the kth power. So we want to know what this matrix raised to the k power is equal to. So let's call this matrix M. So we want to calculate M to the k power. And one way to do it is to just keep multiplying. Okay, this is a nice, simple 2 by 2 matrix. But it also helps to keep in mind that this matrix M, if you look at the first and second columns, you can see that this first column, 0, negative 1, is what you get by rotating the vector 1, 0 clockwise by 90 degrees. And if you rotate E2, which is 0, 1, by 90 degrees clockwise, you also get 1, 0, which is the second column. So this matrix rotates the plane clockwise by 90 degrees. So to calculate M squared, so let's write M again. It's just this matrix. M squared is going to be what you get when you rotate E1 and E2 by 90 degrees twice. So that's rotating clockwise by 180 degrees. So 1, 0 is going to go to negative 1, 0. And 0, 1 is going to go to 0, negative 1. So that's M squared. And M cubed is going to be when you rotate 270 degrees. So 1, 0 is going to go to 0, 1. And 0, 1 is going to go to negative 1, 0. M to the fourth is going to be what? Well, if you rotate by 90 degrees 4 times, you do 1 full rotation. And that just keeps the plane where it is. So you just get the identity matrix. Again, you could just multiply M by itself a bunch of times and see that this is what you get. But this is a nice geometric way of explaining where these come from. So now you can see that if you do M to the fifth, okay, that's just M to the fourth times M, that's just going to be M. So this is going to be M to the fifth. M to the sixth is going to be M squared. M to the seventh is going to be M cubed. M to the eighth is going to be M to the fourth. It just cycles every 4. So this is going to be M to the ninth, and etc., right? So those are the powers of M. Okay, so now we're ready to use the formula, use the definition of the matrix exponential. So E to this matrix T, remember that's by definition I plus mt plus m squared t squared over 2 factorial plus m cubed t cubed over 3 factorial, etc. So let's write out what you get. So this is going to be the identity matrix plus m t. Oh, I didn't factor out the b. So I actually have a b here. Like that. Okay. Right? Because my M was the matrix without the b in it. So I'm going to get this plus M bt plus m squared bt in parentheses squared over 2 factorial plus m cubed times bt cubed over 3 factorial plus, and then I'm going to get the identity matrix because that's m to the 4th power times bt to the 4th over 4 factorial, and then I'm just going to get, m times bt to the 5th over 5 factorial, and it's just going to keep going on in that pattern forever. So now let's look at what you actually get. So this is a 2 by 2 matrix you get, right? So let's actually see what the individual entries are. So let's look at the 1, 1 entry on the top left. What is that equal to? So for the top left entry, look at what I'm adding. I have 1, 0, -1, 0, and I'm going to get 1 again. So it's going to alternate between 1, 0, -1, and 0, and it's just going to keep doing that forever. So the sum for the top left, I only need to look at the entries that are not 0, right? So I'm going to get 1, then I'm going to get 0, and then I'm going to get minus bt in parentheses squared over 2 factorial, and then I get 0, and then I get a 1 times bt to the 4th power over 4 factorial. And then I'm going to get a minus bt to the 6 factorial over 6 factorial. Bt to the 6th power over 6 factorial. And it's just going to keep alternating between plus and minus forever. Well, if you think about what that is, do you recognize this series? It's even powers. It's cosine. It's the Taylor series expansion of cosine. So this is going to be cosine of bt. Let's look at the 1, 2 entry. So this is the entry on the top right. So if you look at the entry on the top right, okay, you start off with 0, and then you have a 1 bt, then you have a minus bt in parentheses cubed over 3 factorial. So you only get the odd powers, and they alternate between plus and minus. So you're going to get bt minus bt cubed over 3 factorial plus bt to the 5th over 5 factorial minus bt to the 7th. Why is my pen doing this? To the 7th over 7 factorial, etc. Well, what is that equal to? That, I hope you recognize, is the Taylor series expansion of sine. So this is going to be sine of bt. So that's a really nice result. And the 2, 1 entry, so the bottom left entry, well, if you compare the bottom left entry, I have 0, -1, 0, 1. They're just negative of the entry on the top left. On the top right, right? Because everywhere on the top right there's a 1, on the bottom left there's a -1. And on the top right, when there's a -1, on the bottom left there's a 1. So it's just negative the 1, 2 entry, that's negative sine bt. And similarly, when you look at the 2, 2 entry, okay, notice that the 2, 2 entry on the bottom right, these numbers are the same as the blue numbers. So I just get the same as the top left. So that's going to be cosine bt. So now we know the answer. We know that e raised to this matrix times t is e to the at. So where did we get this e to the at from? We got it from here. And then we know what this is, the other part. That is going to be cosine bt, sine bt, negative sine bt. Negative sine bt, sine bt, cosine bt. Okay, let's put this in a box. So that is the matrix exponential for that matrix. So let's put it all together. So if you have e to the at, where a is your PCP inverse, that is just going to be p times, so p was this matrix, remember, where the columns are u and v. U and v are the real parts of one of the complex eigenvectors. And then you have this e to the at cosine bt, negative e to the at sine bt, e to the at sine bt, e to the at cosine bt, and then whatever p inverse is. So u was the real part of that complex eigenvector phi, and v was the imaginary part of phi. Okay, I think that will do it for this video. In the next video, I'm going to do a few examples of calculating these things out.